9 billion light-years away, a powerful bomb is ticking. When it explodes, even the nuclear reactions in our sun will stop. Even crazier, the bonds between every atom in the universe will break, and in the blink of an eye, everything will be gone. And I'm not even kidding. Recently, astronomers found two supermassive black holes. They're 99% of the way to crashing into each other. If these two supermassive black holes collide, the energy released could seriously mess up the universe's space-time fabric. Whenever two black holes collide, the collision throws out millions, even billions of times more energy than the sun, in the form of gravitational waves. And just imagine, these recently discovered black holes are 150 million times bigger than our sun. What could happen? Could the energy from this collision reach Earth? Well, we'll find out in today's video. So, first, let's understand what's going on. Well, astronomers at the California Institute of Technology, also known as Caltech, in Pasadena, California, recently figured out that one of the supermassive black holes in a pair they found, called PKS 2131-021, is actually a highly energetic blazar. This object is 100 million times bigger than our sun. Basically, as we all know, SMBHs, or supermassive black holes, can be millions and millions of times bigger than our sun, and they usually become quasars are SMBHs that shoot out extra matter at the speed of light, like a jet stream. Now, if a quasar's jet stream points directly at us, at Earth, it's called a blazar. And today, one such blazar is about to merge with a smaller black hole. But let me tell you, this isn't the universe's first binary black hole collision. A similar event happened 3.5 billion light-years away, in a galaxy called OJ 287. This galaxy has at least two giant, closely orbiting SMBHs. One weighs as much as 18 million suns, and the other is much smaller, weighing around 150 million suns. Astronomers have studied their movements for 3 to 4 decades. For a long time, we only knew that the smaller black hole orbits the larger one every 12 years. In this 12-year orbit, the smaller black hole passes through the larger one's disk twice, creating two expanding bubbles of hot gas in a flash. And as a result, its brightness becomes 4 times greater than our entire Milky Way galaxy. By detecting these flashes, astronomers can predict the binary system's orbit. Using this method, an Indian astronomer, Lankaswar Day, predicted the orbital period of this binary system in 2018. He was working as a researcher at the Tata Institute of Fundamental Research in Mumbai. Actually, even before him, astronomers worldwide had been working on this since 2010. But because those two flashes occur randomly within a 12-year period, we couldn't understand the orbit's pattern. Astronomers tried hard and even built a model based on data collected since 1975, but it was only accurate to within 2 to 3 weeks. Meaning, when they predicted the first flash in December 2015, they only gave the month and year, not the actual date. But finally, in 2018, Lankaswar Day created a model based on his independent research that predicted the exact date, July 31st, 2019. The date was set. All that remained was to wait for the day and the observations. But before observations could begin, a new problem arose. In July 2019, the sun came directly between the OJ 287 galaxy and Earth. Because of the sun's brightness, capturing a small flash so far away wasn't possible for any telescope on Earth or satellites in orbit. Day had lost all hope, but then something special happened. NASA's Spitzer Space Telescope, which was going to be decommissioned the following year, was orbiting 254 million kilometers from Earth. Luckily, it had radio wave detectors that could record the flash. Hope soared, and on the day Day predicted, the flash was finally observed. Day's orbital model was perfectly accurate. This could also verify whether the black hole binary PKS 2131-021 is on a collision course or just an illusion. It might be an illusion because, unlike the black holes in OJ 287, no flashes had been seen in PKS 2131-021. But because the larger SMBH is a blazar pointing its jet towards Earth, Caltech astronomers didn't need such a flash. Caltech Research's lead author, Sandra O'Neill, and her mentor, Tony Reedhead, found a different but similar method. They started regularly observing the blazar's light. After a few days, They noticed the light periodically brightened and dimmed at 2-year intervals. That means there's probably another SMBH orbiting the blazar. Further research revealed that these two SMBHs are 100 times closer than those in OJ 287. After orbiting each other for 100 million years, they're now 99% closer. And not just this, they only have 10,000 years left before they collide. How do we know this? Well, just like OJ 287, all known quasar mergers have been studied for the past 45 years, not just recently. From 1975 until now, 5 different radio observatories worldwide have recorded about 1,800 quasars. These studies suggest that at the rate they're orbiting and getting closer, they only have 10,000 years left before the final collision. As we've seen, all black hole collisions emit energy as gravitational waves. Caltech and MIT control LIGO, the Laser Interferometer Gravitational Wave Observatory, in addition to their radio observatories. They even made such an observation in 2015. So why aren't we trying to detect them? Let me give you an example. Suppose you're swimming in water. Can you easily detect high tide or normal waves? Obviously, normal waves, because their frequency is high, and the distance between two waves, the wavelength, is short. But with high tide, the wave frequency is low, and the amplitude is very high, making it hard to detect. And that's the problem with LIGO, whether it's Caltech's or NASA's upcoming LISA, Laser Interferometer Space Antenna, planned for launch by 2034. Both instruments can only detect mergers up to 200 solar masses. Black holes heavier than 100 million solar masses emit low-frequency, long-wavelength gravitational waves. These waves won't harm Earth. Nobody's going to die. The frequency of the gravitational waves from such a large black hole will be so low and the waves so big that our entire Earth will float on them, and we won't even know. Isn't that interesting? Now you might be thinking, those black holes are 9 billion light-years away, so they might have already collided, and maybe we're currently floating in the gravitational waves they produced. Who knows? Well, those who want to detect these waves can follow the International Pulsar Timing Array, IPTA project, of which India is a collaborating member. This project uses 4 observatories: the European Pulsar Timing Array, EPTA, the North American Nanohertz Observatory for Gravitational Waves, NanoGrav, the Indian Pulsar Timing Array project in PTA, and the Parkes Pulsar Timing Array, PPTA. They'll use rapidly spinning millisecond pulsars like lighthouse lights to detect low-frequency gravitational waves. Millisecond pulsars are neutron stars that rotate incredibly fast, and their light pulses blink more accurately than atomic clocks. If even a tiny gravitational wave passes between Earth and a pulsar, space-time bends, and the pulsar's light takes longer to reach us because of the curved path. But there's a catch. Even though pulsars are precise timers, they're unstable objects themselves. So how do you think the IPTA project will tackle this problem? Share your answers in the comments below. If I find the answer correct or logical, I'll pin it. See you next time, friends. Till then, as always, stay curious and keep learning. Jai Hind.